Good morning. We have discussed in the last class that we're just about to discuss the different. I remember the different isolation techniques which are used in ICs. I spoke of the junction isolation. Remember? Then I spoke that how the junction isolated IC can be converted in oxide isolation. That means I called it low cost process. Local oxidation, all is called oxide isolation. I told you that though the junction isolation was the most popular process in the early phase of integrated circuits, particularly bipolar integrated circuits, whose frequencies were limited to several megahertz only. But as the technology proceeded, the demand also increased, and you know today that ICs with frequency ranges, say up to hundreds of megahertz, is commercially available, as well as hundreds of megabits per second in the digital domain. And also you have heard of gigabit per second kind of operation for very high frequency, high speed ICs. Junction isolation did not serve the purpose because of the lot of capacitance involved with the different islands, which ultimately, due to the very large capacitive leakage at high frequencies, prevented the use of such ICs to very high frequency, high speed applications. Thereafter, you remember that the sidewall component of capacitances, which constitute the maximum value of capacitance, were reduced or almost eliminated by the use of oxides to substitute silicon between the islands. This point I discussed in the last class. So just go briefly what I told you in the last class. I told that at the end of such oxide isolation, So you see that this is the end result at the end of oxide isolation process. You see that here the N island, two adjacent N islands which were formed by epitaxy. Initially this layer N type was formed by epitaxial technique above the p-type silicon substrate in bipolar technology, and afterward, of course, in this MOS technology, this epitaxy was not necessary in the first phase. Only at the end of the MOS evolution, when CMOS came, the very latest CMOS, again epitaxy has returned into the field of CMOS technology, MOS technology. Otherwise, epitaxy was essential only in bipolar technology. And if you just have a P plus junction here, P plus, N separated by P plus, and the substrate is also P, the drawback was mentioned in the last class. There is a lot of capacitance because of very narrow depletion layer at these edges due to higher doping. I told you in the last class. And this has now been eliminated almost fully by replacing the silicon here by a silicon dioxide film, silicon dioxide layer, which is a very good dielectric, very good insulator. And the technology is such that ultimately at the end of the process, the planarity is maintained. More or less at the end of the process, the average silicon plane and the oxide region plane, at their location, they are almost the same. That is why this is also called an isoplanar process. This is also called an isoplanar process. This is important for photolithography. You remember that what I said, I told that initially about 50% of silicon thickness of the epilayer thickness is etched off by selective photolithography and etching. Thereafter, a wet thermal oxidation is carried on till the surface of the oxide becomes almost isoplanar with respect to the surrounding silicon plane. Okay, the surrounding silicon plane and this oxide, they become isoplanar with respect to each other. And you see now this the P plus region between N and N islands, they are replaced by an oxide, and this is what is called, the same is called fully, there are many names that nowadays in ICT, this MOS technology, this process is called fully recessed oxide isolation. Fully recessed oxide isolation. But as you know, the demand of the silicon ICs have not been limited to only several tens of megahertz or even several hundreds. People are now, developing ICs for very high gigabit capacity. And there even this kind of oxide isolation is not effective. There should be some other means. What is the drawback of oxide isolation? You see that, yes, the sidewall component of capacitance has been almost eliminated, but there is still some capacitive leakage, but that will be very small. But the bottom component of capacitance is still there, which is not very, very small. The capacitance of PN junction in the bottom region, in the lower surface, that still remains, and therefore for very high frequency operation, there is limitation. I should also be able to reduce this capacitance, which occurs at the bottom. So many things have, many suggestions as well as technologies have come forward. And in general, these technologies are named as SOI process or SOI technology. SOI. Full name is silicon on insulator. Silicon on insulator. The first attempt, and of course very expensive attempt till today, that is the most expensive, of course very most effective silicon technology, and that is called SOS. SOS is nothing but a very special case called SOS is nothing but a special case of SOI. This is silicon on sapphire. silicon on sapphire. What is sapphire? Sapphire is nothing but alumina crystal, aluminium Al2O3 crystal. So if you have a piece of sapphire like this, Al2O3 crystal, this is what is known as sapphire. Okay, and on the top of this sapphire film, sapphire crystal, which is not something like a single crystal of silicon wafer, but it is transparent. Silicon, you know, you have seen silicon wafers. They are not transparent; they are blackish type of grayish colored. Whereas sapphire is a very precise, you know, the very precious stone, which is used, you know, by the, you know, for rings, etc., or as jewelry. And you know that sapphire, the red sapphire is nothing but chromium doped sapphire. Just the doping of certain impurities changes the colors of sapphire material. It's a very expensive jewelry stone, okay? But in our microelectronic applications, we are using sapphire as a substrate, okay? Very expensive substrate. On the top of this sapphire crystal, you can grow an epitaxial film of silicon. That is why called silicon on sapphire. You can grow an epitaxial film of silicon, crystalline film of silicon, with very good lattice matching. This is possible. Certain direction, crystal directions of sapphire and certain crystal directions of silicon, they match quite well. So you have to find out which two directions are okay for crystal matching. You can grow on this a silicon film, all right? And this silicon film can be now photolithographically separated into small blocks or islands, something like this. This is silicon. Silicon epitaxial film. By epitaxy, I mean a crystalline film properly ordered without any lattice discontinuity. From alumina to silicon, the lattice matching is still there, and it is a silicon film, and it can be doped or undoped according to you. So what you do, you first grow an epitaxial film of silicon on this sapphire substrate, then photolithographically define silicon islands or silicon blocks, and into each silicon block you grow your component. Maybe in a particular application, here I grow a transistor, bipolar junction transistor, here a CMOS, and here a resistor, maybe in a BiCMOS technology. You know, in BiCMOS, we grow both bipolar transistors and MOSFETs together, along with resistors and other components. So let us consider that we can grow here a bipolar junction transistor. This island may be dedicated for a CMOS or an NMOS and PMOS separate. That's up to you. And this one may be for a resistor. And thereafter, you do the same thing as you did normal technology. You etch windows for contacts, metallize, and etc. Only thing is, the surrounding region, this is all filled up by a very high quality dielectric film. Everything is surrounded at the end of the process by a very high quality dielectric film. So do you know what is the end result? What is the good thing about it compared to the earlier one? Here is the bottom layer component of capacitor that is also eliminated almost to a very great extent. So these things ideally should be able to go to very, very high peak and frequency, high speed, depending on whether it is an analog circuit or a digital circuit. And this is a very, very advanced thing. Unfortunately, silicon on sapphire came with a great promise. But ultimately, I find that if you just review papers, all recent publications as well as within the last 5 years, you do not find many papers on SOI, SOS. The reason is it is technologically very tough. And quality of the silicon film, which is grown by a process called heteroepitaxy, the process which is used called heteroepitaxy. Hetero. Heteroepitaxy, not homoepitaxy, because the two materials are different. This is silicon and this is the alumina. Therefore, this epitaxial process is not an ordinary epitaxial technique, it's a very specialized epitaxial technique, and there will be always some crystal mismatch. And as a result, in the interface cannot be as good as in a silicon ordinary epitaxy. And as a result, the mobility of such films is always inferior to that in crystalline silicon, ordinary crystalline silicon. The mobility of the silicon films, which is very important for high speed, the electron and hole mobilities in this epitaxial film, heteroepitaxially grown silicon film, is rather poor compared to that in crystalline silicon. And that ultimately limits the speed of operation, the frequency of operation. And then the technology itself is very expensive, and alumina crystal growth itself is a very expensive process. And therefore, what people are now predicting, that this one perhaps will be used only for space applications or very specialized military applications where we require a very high order of radiation hardness. What is radiation hardness? Radiation hardness means that when such any IC or any circuit, any device is exposed to external radiations, these radiations may be radioactive rays, these radiations may be, that various RF and high frequency waves in which we are submerged today in the days of this so-called huge communication things. And also it may be cosmic ray particles. All these radiations are impinging on whatever our human body, all electronic components, all machines, and particularly when you are thinking of MOS and CMOS, which is a surface controlled, which is surface phenomena devices. Everything occurs at the surface in MOSFETs. You know that any damage induced at the interface or any excess carrier generation which happens due to the extra radiation which falls on the substrate, and that leads to device failure. This is what is known as radiation effects on integrated circuits. And people try to make radiation effects, that the ICs, as hard as possible so far as radiation effects is concerned. These are called rad hard ICs. Rad hard means radiation hard ICs. From radiation hard point of view, it is found that this material is excellent. Why? Because as some external particle or wave enters through this, it is penetrated, not only confined near the surface, it penetrates into the material. And because the bottom material is an insulator, you don't have much problem, because even if there are some electron holes generated in the insulator, they are not available in the semiconductor. But whereas on the other hand, if you do not have such alumina crystal in the bottom as compared to the other one, that here the entire thing is silicon. The radiation penetrates to the bottom, and lot of electron hole pairs are generated, and which affects the circuit operation, as well as more damages are created because of, in this case, this chance of damage as well as the so-called radiation-induced currents and other bad things cannot occur. And therefore, people are saying that this expensive technology perhaps will be confined to the future space applications and very specialized military applications. But you know that there have been some intermediate solutions. And that is why the general name which was given SOI, this is a general name, okay? And this is the extreme solution. SOS is the extreme. You just start with an insulating substrate on which you grow a silicon film. You can do something else. What you can do is as follows. You take a silicon substrate, on which you grow an oxide, silicon dioxide, by the process of simple thermal oxidation. Okay? Then on the top of this, you again grow a silicon film called polycrystalline silicon layer. Polysilicon. In the language of technology, you call it polysilicon. On the top of this oxide film, you deposit a polysilicon film of thickness around 5,000 angstrom, 3,000 angstrom, 1 micron, depends on the technology, whatever you are using. Typically today around 3,000 angstrom. You grow a 3,000 angstrom polysilicon layer on the top. What is polysilicon? Polysilicon is nothing but polycrystalline means it consists of small crystals of silicon. But their size, on the average size is very small, of the order of 1 micron or even less than that. So polycrystalline film means it is nothing but small crystals of silicon. They are bonded together in arbitrary orientations. They are not uniformly oriented. Okay? And then after the deposition of the polysilicon film on the top of it, you sweep a high power laser on it. On this, what you do, you arrange to put some high power laser, high power laser. This radiation from the high, I have not shown here till now the polysilicon film. I will show the end diagram because of my limitation here. So there is a polysilicon film. On the top of this polysilicon film, you sweep a high power laser. This high power laser locally melts the polysilicon. High power pulse lasers is not a continuous laser, so that average heating is less. Heat is a local heating, both in time and space. As the high power laser sweeps across two-dimensionally, of course, you have to make a two-dimensional raster scanning. Then what will happen? This molten silicon propagates along the surface. And a technique called zone refining and melting cum resolidification takes place, and which ultimately produces a crystalline silicon film on the top. Initially, I started with a polysilicon film, and afterward, it is called laser recrystallization. This technique is called laser recrystallization. Laser recrystallization. This is what is known as laser recrystallization. So this polycrystalline silicon film is converted into crystalline silicon film. Why do we do that? Because polysilicon film has got inferior electrical properties. Its mobility is extremely small. Electron mobility maybe as low as only 10 centimeters square per volt second. And hole mobility is extremely negligible. And that is totally undesirable. And if you convert this polycrystalline film into a silicon crystalline film, mobility improves. Again, we get mobilities, electron mobilities around 1000 centimeters square per volt second, and hole mobility is around 300 to 400 centimeters square volt second, almost close to the bulk silicon. And this silicon now can be photolithographically etched into islands, just like this. So at the end, what we do, after the polycrystalline film is converted into crystalline film by laser recrystallization process, then photolithographically we etch blocks as indicated earlier. So these are crystallized polysilicon films after etching. After photolithography followed by etching, we get this. So these are, this can be now doped, and whatever process you will normally adopt in silicon fabrication, IC fabrication, you can do. And you know that you can now have a transistor here, a MOSFET here, a resistor here, or all MOSFETs in MOS technology, or a combination of bipolar transistors, diode and resistors in bipolar technology. That's up to you totally. Or combination of transistor BJT and MOSFETs in BiMOS or BiCMOS technology, that's up to you. And ultimately the same thing, only difference between this one and the earlier one, the SOS, is in the SOS the whole thing was sapphire. Now it is mostly a silicon substrate, a low cost material. The silicon substrate is a batch production technique and the cost wise is much smaller. Then we have a separation of a dielectric film, a very good quality dielectric silicon dioxide. Its resistivity is very high, very low loss material, up to very high frequency. And on the top I have these silicon islands, and in each island we have our components, and we can do the similar IC processing to finally get our final IC, final product. By this process also, not only we have eliminated almost fully the sidewall component of capacitance, but also we have eliminated to a great extent the bottom capacitances. But have we been able to eliminate the bottom layer of component of capacitance fully in this case as compared to SOS? SOS, there is no conducting thing in the bottom. But now, so there will be some MOS capacitors present here. MOS means the top one is not metal, but another semiconductor, then oxide, and then semiconductor. So there will be some capacitance. But if this thickness is around 3000 angstrom, this capacitance is so small, and the overall each component area is today of the order of microns, by microns. So this capacitance can be reduced to a very great extent, and ultimately, therefore, people are saying that this process technique is, in fact, today product is available using such SOI products, which operates up at 500 megahertz gigabits, or even up to several gigabits per second. Such products are available. Okay. Of course, the conversion of the polycrystalline silicon into crystalline silicon, as I told, this is by laser-induced process. There are other processes also. One plus the RCA group, Radio Corporation of America, USA. RCA group, they developed a technique called moving heater technique, graphite heater. Instead of using a high-power laser, what they did, they had small graphite wires, which are red hot, very highly heated by passing electric current, and the wafer sweeps around it like this. And by that process also, they reported very good quality wafer, but laser is now more standard than the other technique because of the advantage involved here. Some people have also used electron beam recrystallization. Many intermediate research work have been reported, but ultimately it has been found that the laser recrystallization is the best technique. But in the meantime, some other fellows, they proposed another nice idea apart from this one. Here, that recovering this from polycrystal to a single crystal, a very high quality single crystal, is a rather difficult job. That means achieving a very high mobility is a very difficult job. So some other people said that let us follow another technique. What they did? They started with, say, again a silicon substrate. Okay? And then they implant oxygen atoms, ion implant, oxygen ions, called oxygen implantation. Heavy implantation of oxygen ions at a dose of around 10 to the power 18 ions per centimeter square. So on the substrate, you implant a oxygen ions at a very heavy dose, 10 to the power 18 per centimeter, ions per centimeter square is a very heavy dose of implant. Then what happens? Oxygen ions are penetrated quite deeply into the substrate. At the end, it is found the oxygen ions more or less distributed like this. There are a lot of concentration in this region, in this surface, slightly deeper from like this. This is the oxygen atoms distribution. You remember the typical distribution in ion implantation is the peak of distribution are not at the surface, rather a little bit deeper. Whereas in the surface the concentration is reduced. It is something like this. So if I draw it like this, it will be something like this, the distribution. You remember that that is a typical distribution in ion implantation. Now, after this very heavy ion implantation, heavy oxygen ion implantation at a dose typically around 10 to the power 18 per centimeter square, if you do some annealing, annealing means high temperature treatment. People today are using a technique called transient annealing or rapid thermal annealing, RTA. Rapid thermal annealing. Rapid thermal anneal. Rapid thermal anneal, RTA. That means the peak temperature may be very high, around 1300, 1400, almost near melting point, but the average temperature is very low, so that the duty cycle is very less. And as a result, it can be shown that these oxygen ions can be bonded very nicely with silicon to form SiO2. So effectively, at the end of the process, when this is over, you get more or less a good quality of silicon dioxide buried. This is what is called buried SiO2. And even these, there will be few oxygen atoms here. They will be, either removed by the out diffusion, because oxygen being a gas, they will be removed by out. But just below the surface, several thousand of angstroms below around 3000 below the surface, we get a silicon film where there is, of course, a little oxygen doping. Definitely, there will be little oxygen doping. But this film is usually, that after implantation it will be highly damaged, because the oxygen atoms will damage the silicon film, will distort the lattice, and we say it will amorphize the surface. We say normally, technologically, we say the silicon surface gets amorphized, means it becomes highly disordered. The silicon becomes highly disordered. And after annealing, of course, after the rapid thermal anneal, of course, not only the silicon dioxide formation becomes very proper, but also the film on the top also recovers greatly from the damaged condition. It becomes a very good crystal. Its mobility is recovered. Annealing recovers not only the damages, but electrical properties are also recovered. Remember, in silicon, unless the impurity atoms are substitutional impurity atoms, unless they occupy vacancy sites, they do not contribute the electrons or extra electrons or holes. It's called electrical activity of silicon. Depends on whether the impurity atom is a substitutional, occupies a substitutional site or an interstitial site. But after implantation, which is a non-equilibrium process, most of the impurity atoms, they normally occupy some bad interstitial locations. Okay, and as a result, there will be, that you don't get the electrical activation. So therefore, of course, these oxygen atoms are not meant for doping. This is meant only for oxide thing. But still, the annealing recovers the crystal to a great extent. And sometimes what we do, we also grow an epitaxial film on the top. Silicon, it is a homoepitaxial. This is not a heteroepitaxy. And you can create an excellent quality silicon film on the top as compared to the previous one. The quality of silicon film which you can achieve now is much better. Of course, there are competitions. This group says ours is better, and this group, both groups are working. Till today, they are working hard. They are competing very greatly. They are great competitors. And these groups, some people still say no, our films are better. But this one, of course, some Japanese group also have jumped on it. And they are saying this is perhaps a better process. SIMOS and all these things, names have been given. SIMOS, SIMOS, etc. names have been given. And again, by the same technique of photolithographic etching, you can grow your IC. So this SOI process today, there are three things. One is the old SOS, which is good, but has very limited applications due to reasons which I've already told you. Second is SOI, means one is recrystallized polysilicon on oxide, this one. And the third one is called buried oxide process, buried silicon dioxide process. Some people have also tried with buried nitride. Instead of oxygen implantation, they have implanted nitrogen and tried, but it is a very difficult process. Buried nitride has not been so much successful. On the other hand, buried oxide has been very, very successful. So this is the latest technology. So far as isolation of components for the fabrication of an integrated circuit or in general VLSI is concerned, the status of electrical isolation is this. It started with junction isolation, which is the simplest. Till today, many bipolar integrated circuits are made using ordinary junction isolation. But the modifications came thereafter. First one is is called oxide isolation or low-cost process. Let me tell you, 99% of CMOS products, whatever you are seeing in the market today, even you are using in your projects, they make use of the oxide isolation technique. Another 1% is special applications, where for very high speed. So maybe in that 1%, another 1% in 1%, people for defense and space applications, that is SOS, and remaining 90% in 1% is either this technique or this technique. But this technique has been finally found to be more potential, to have more potential than the older one. To get a very excellent quality oxide silicon film here is difficult. Some people, what they have tried is, that they have etched oxide. Suppose here, if you etch the oxide, remove the oxide, all right? From here, you remove the oxide. Problem, I think you understand my limitation now. I cannot wipe it off as on the blackboard. So I just remove the oxide from here and then grow this polysilicon film and then do the laser sweeping. Then what happens, the crystalline order just here, because there is a polysilicon film just deposited like this. So from this crystalline order, there is a nucleation starting. That just above this single crystal, the crystal atoms, the other polycrystal atoms, the silicon atoms, they arrange themselves. And from there, it grows. It is called lateral epitaxy. From here, the epitaxy develops this way and that way. It's called SID. For any successful epitaxy, you start a nucleation. Normally in homoepitaxy, why it is so good? Because my silicon is a substrate where atoms are beautifully arranged, and on which, when the incoming silicon atoms, they also try to get the same lattice positions, where the potential is minimum. And that opportunity is not available on the oxide, which is an amorphous film. But if you provide some space from which it gets the starting nuclei for the growth of epitaxy, then one can get a much better film. So that has been done. The oxide, after etching, oxide is not fully cover the surface. It's not fully covering the surface. Rather, in certain locations, there are strips. Already bare silicon is available. Then you grow polysilicon, then sweep the light beam, the laser beam, and ultimately you get better quality films. So this is, as I told you, that this is still research is going on, but commercial products are available using both these techniques for very high-speed spatial applications.
Sir, How is that polycrystalline film deposited on that SiO2 layer?
Okay, as I told you that, yes, I am not going into the details of technology because of the limitation. I have to teach other things. But anyway, because you have asked me, I'll answer that question. The usual technique is you crack silane gas. Silane is SiH4, silicon hydride. Okay. If you take the silicon substrate or alumina substrate or oxidized silicon substrate, whatever the case may be, and put it in a high temperature furnace at a temperature around 1050 degrees centigrade, 1050 degrees centigrade, then introduce silane gas, SiH4, mixed with enough amount of hydrogen, okay? Then as the silane comes close to the substrate, which is kept at 1050 degrees centigrade, the typical temperature, it decomposes into silicon and hydrogen. These silicon atoms, after their production, after their just formation, they get attached to the silicon surface, and there is called a movement called surface kinetics. Silicon atoms start moving on the surface. And ultimately, they get adhered to a particular site, and this process is chemically known as adsorption, ADSORPTION, adsorption. So a site. And again, even under adsorbed condition also, it starts moving because of the high temperature. And finally, it has to stop somewhere. Where it will stop? A position where the potential is minimum. And where is the potential in minimum? Just above a lattice atom, because that's nature has created like this, isn't it? The locations of the crystalline atoms, they are nothing but the points where the potential is minimum. So these are called nucleation king sites, and all these names are there. And that's why it has been shown that layer by layer you deposit good quality film for epitaxial growth. But if it is an amorphous silicon, I would say is an oxide layer, is an amorphous oxide, is not silicon. Then in that process, it is not getting regular nucleation sites. Therefore, the growth will be random, and we get polycrystals rather than. And if you do the same deposition at a very low temperature, around 500 degrees centigrade, the film is amorphous in nature. The order, there is practically no order. So therefore, what people do for polysilicon growth, normally the temperature is around 750 degrees centigrade. Whereas for epitaxial growth from silane, the temperature is typically 1050 degrees centigrade. There are other alternative sources like silicon tetrachloride, SiCl4, dichlorosilane, SiH2Cl2, etc. So these are the technical details. Many things are there, and I don't think there is much scope to teach them in detail. What I will be doing here, I will give you a very brief account of the IC technology in the sense that is required in the circuits. To understand the circuits and systems, you need a little bit more information about the IC technologies. That's why I'm just telling. For details, I'll refer to a book, say, called Vlsi Technology by SMC, is a dedicated book. Or even, I think you can see the Millman Halkias one chapter called IC fabrication or device fabrication. There is one chapter in Millman Halkias' book called device fabrication. That's a nice chapter. I would request you to go through that particular chapter. It gives you a lot of information. Okay, I think, yes, please.
The oxygen atoms around the buried layer, do they affect the performance?
Yes, yeah, it's a very right question. And as I told you, this is a research topic till today, and people are improving and improving. What I say that as you annihilate, two things happen. Firstly, the oxygen distribution, though it will have a tendency to disperse because of the redistribution, thermal diffusion, but because the bond formation, there is a reverse process by which there is a conglomeration of the oxygen atoms, and that try to form all the silicon bond, SiOO forms the SiO2. Double bonds, Si, two double bonds, OO, form the SiO2. And that is, it will try to form. But in spite of that, many oxygen atoms will be there in this thing. And these oxygen atoms, some of them will act as recombination centers and traps. And that kills lifetime. And if the lifetime is kill, you know that bipolar transistor, particularly if you make bipolar transistors, gain will be less. Okay, these are some problems. So what people have done investigate a lot of experiments and then some reverse thing, how to remove that oxygen atom, etc. And now the status is such that yes, we can get a very, very high quality film with a mobility, electron mobility close to 1000 centimeters, 800 is typical, people have reported, 800 centimeters square per volt. One thing is electrical parameters. If I am satisfied, I don't bother whether the oxygen is there or not. But typically, people by many experimentations have been able to achieve mobility, electron mobility around 800 centimeters square per volt second, which is fairly good for such a good film, for a very thin film. Remember, the film thickness is around only 3000 to 3000 angstrom today. 1000 angstrom to 3000 angstrom. And all techniques are ion implantation. They don't use any diffusion technique for impurity introduction. So I think time is over today. And tomorrow tomorrow is the next class, I'll discuss about the basic technological steps in bipolar and